Hello, thought I'd make a quick video here about the new Risc-V system I put together. It's based on the new CH32V307 RISC-V. I saw it on JLC Parts Division LCSC. They were selling a little $10 development board, and I noticed they were having a contest. I was thinking, well, you know, I'm not so interested in their contest, but I wouldn't mind getting a few of the parts and throwing it on a board and playing around with it. Check it out. So I did, and this is the board right here. This has the CH32V307 RISC-V. And it's turning out to be a pretty nice little chip. The price was right, is just under $4, about $3.85, something like that. Bought 5 of them, and it has quite a few peripherals inside. In fact, it's chock full of peripherals. To start with, it has 256K of flash, 64K of SRAM, 2 A to D converters. The one that I've used that I'll demonstrate here, it has 16 E to D inputs, 2 DAC outputs, 10 timers, 4 advanced and 4 general purpose, and 2 basic timers, 8 UARTs, some of them are USARTs, 3 SPI, 2 I2S, 2 I2C, USB on the go, USB high speed, plus an internal PHY, not bad. 2 cans, yeah. Real-time clock, 2 watchdog timers, 4 op-amp interfaces, random number generator, an SDIO. The one I designed on here has it's a 4-bit SD card, micro SD card interface. Has a static memory controller for external memories, a video port for low resolution cameras, Ethernet, 1 gig MAC, but it has a 10 meg PHY. At least that's what it says here. I don't know. But quite a few peripherals. Has a hardware floating point support as well. So not bad for under $4. I'm liking it. What I thought I'd demonstrate here is I've taken 4 potentiometers and interfaced each of those to a to D converter channel. What I've done is I've taken the digitized potentiometer value, and from that 0 to 4095 value, generate a 0 to 100% duty cycle value. That duty cycle value I use to update an internal timer register that generates the PWM output, and so I use 4 timers to do that. Each one drives an LED that's on this board here. This, by the way, this is a Fpga board based on a Trion T20 from Phoenix. Not a bad little Fpga. It has 20,000 logic cell elements. Very economical. I think in this particular package, it's the QFP 144. They're about $12-13. I think it's what I bought it for. I've used it in the past in the 256 pin BGA package. I think LCSC sells them for like $8-9. not a bad price for FPGA with 20,000 logic cells. That's just not bad at all. And they do have double data rate I/O, and that's where I put in a 16 megabyte Hyper RAM IC right here, and I'm going to take advantage of the double data rate I/O and write some Verilog to interface to it. Also on this board is a FT 4232. It has 2 multi-protocol serial engines plus an additional 2 UARTs. One of the multi-protocol serial engines I use as a SPI interface. I should say that Evenix uses that interface for programming the flash with the bit stream that the FPGA needs. The other multi-protocol serial engine is used for the JTAG interface. I don't use that on the Trion FPGAs, not right now. I primarily use just the SPI interface and download the bit stream that way. Seems to work just fine. So over here we have the 307, which is how I'll refer to the CH32V307 RISC-V, and this is the Trion T20. I'll refer to it as the T20. You know, I don't have to say all these numbers and letters and everything all the time. So with my potentiometers here, I will vary the duty cycle and light up my 4 LEDs. There's a red, a green, a blue, and a yellow, and that's just really it's to demonstrate some of the capabilities of the new Risc-V, which is really kind of a cool chip. Oh, by the way, I have some NOR flash here, SPI flash right here for maybe data logging, but if I want to use it for that. So on channel 0 here, I have the red LED, and it should start coming up here. Yeah. These are new boards, and what this allows me to do is, besides have fun, is test out all the tool set in terms of being able to compile both C code, my Verilog for the FPGA, and then make sure I can connect each of them properly, and then download the executable into the MCU flash, and then of course the bit stream into the SPI flash, and hopefully everything's wired right and works, and so far everything seems to be working okay. So here's the green. Turn the red off. I don't want them clashing on the video. The green really lights up good. Yeah. Let's go back to the red here. You'll notice this blue one over here on the processor board is lighting up. That's because that's my test LED, and it's connected to timer output 0. So I got the 4 timer outputs. They pass through my bus system here to the FPGA, and then the logic is real simple. It's just pass through logic to the LEDs. And it's implementing simple little logic like that allows me to verify my tool set. And not so much tool set, but my design. Make sure it's all wired right. And there's my blue. And here's my yellow. Right here, the 4 LEDs right there. Hopefully they're not fuzzy. But so I really like this Risc-V. This particular one here, the 307, it has a maximum clock speed of 144 megahertz. It's not fast, not slow. You know, it's pretty good, pretty nice. I kind of suspect as time progresses, maybe we'll start seeing some of these Risc-V microcontrollers start running into the 200 to 500 megahertz range. A lot like the STM32 line in their H series, like the H745, 747 run up to like 480 meg. It'd be cool to have a Risc-V running at about 400 meg, nice zippy. That'd be cool. But I'm starting to like this part. I like the tool set, the SDK that WCH I think it's Morn River. Yeah, that's the IDE, Morn River IDE, and it's pretty nice. As I look through their sample code, it's easy to understand. It's put together pretty nicely. I don't have a problem with it at all. The A to D converter on this 307 works really well. It's 12-bit, and on this board here, I don't have any filtering. Normally I'll put it like a capacitor, create an RC time constant on a pot, try to minimize noise, but I didn't do it on purpose because I wanted to see how noisy the A to D converter was, and I'm only seeing about half a LSB of noise. It's not bad at all. I'm pretty impressed. It's pretty cool. So I think this Risc-V has a future. Yeah, it's coming along pretty good. I'm liking it. So let me adjust the camera here. I'll put it up on the oscilloscope, check out some PWM action. That's always exciting. I hope that's not too fuzzy. Now let's see. So here's channel 0. It's from 0 to 100%. Actually, there's 100% and there is 0. Lost my trigger there for a second. Channel 1, 0 to 100. How exciting. 100 to 0. So channel 4 is the only one that I have the actual duty cycle measurement for. See if we can get where we can just get 1%. Oh, 0.99%. That's close enough to 1%. Yeah. So hey, this is a pretty, any microcontroller will do this, but that's not the point. The point is it's a Risc-V, and this is my first experience with the Risc-V. I'm kind of liking it. I think it's a nice little microcontroller. Like I said, it'll be interesting to see what kind of speed enhancements are made over the years. Well, that should do it. Before I turn off, I have other little processor boards for my bus system here. This is a ESP32 S2 type. It's gonna be fuzzy. So this is the ESP32 S2 processor board. Has connectors for pass-through. This is a LPC55S69 dual core M33. Basic power switch mode power supply module. The way this works, I just kind of plug these boards together like this and stack them. This is a grow module with I2C mux, real-time clock, battery backed up, little CH32V307 temperature humidity sensor. Actually, it's just a temperature sensor. This is a 2-inch display, and then 0.96 dual display. Just my own little thing I used for development, playing around with, evaluating new stuff. I've got other processor modules in the works. I'm putting together a STM32 dual core system. I should have that in about a week. But I will certainly make some more videos based on what I'm doing with this CH32V307. I think Risc-V's got a future. Well, thanks for watching.